Now, lecture 5 pollutants, continued section under environmental biotechnology. Learning objective is to make the students aware of secondary pollutants that arise mainly from the primary pollutants. And learning outcome is at the end of this lecture, students will learn the following objective, that is define secondary pollutants, how they are formed, and pollution control strategies. So secondary air pollutants like sulfur oxides and nitrogen oxides, they combine with water to form acid rain, and sulfur oxides are primarily responsible for this acid rain. Increase in acid rain correlate with increase in SOx emissions. The highest acidity of the acid rain is found in those areas having the highest concentration of SOx emission. Smog is another secondary pollutant. This term was developed to describe a substance that is a hybrid of smoke and fog. SOx aerosols are one source of smog formation. So what is smog? The sulfuric acid droplets or sulfuric acid absorbed on the surface of soot and fly ash particles can attract moisture from air to form what is often referred to as conventional or classical smog. Such smog, whose principal components are NOx, SOx, and particulates, was prevalent in the coal-fueled industrial revolution before the transportation revolution of the 20th century. So modern day smog is often referred to as a photochemical smog. It is produced by complex sunlight stimulated chemical reactions among the components of automobile exhaust. It is responsible for much today's air pollution in cities such as Los Angeles and Denver. Carbon monoxide from incomplete combustion of automobile engines, particulate matter, and NOx all react to generate the noxious brown haze. An estimated 80% of smogs today arises from vehicle exhaust. Not only does smog smell bad and obstruct the vision, but both short-term and long-term exposure to it may be hazardous. Eye irritation develops upon short-term exposure. Chronic pulmonary disease, asthma, bronchitis, and even lung cancer may result from long-term exposure. In addition, paint and fabrics slowly deteriorate during long-term exposure. Now, solution to a smog problem, we have one thing, that is the catalytic converter, which actually converts any of the carbon monoxide in combustion during combustion produced as a result of incomplete combustion. It also facilitates the combustion of any unburned hydrocarbons to carbon dioxide and water. Finally, it also helps to reduce emission of nitrogen oxides by transforming them into the harmless nitrogen gas. Causes. The problems of smog formation are exacerbated by a meteorological phenomenon known as thermal inversion. Under normal atmospheric conditions, warm air in the vicinity of a large city is trapped by an overlayer of cool air. Since warm gases tend to rise, they normally diffuse upward and disperse the smog and other pollutants. A thermal inversion occurs when the upper layer is a layer of warm air while the polluted air near the ground is relatively cool. In such a situation, the pollutant-laden cool air cannot rise and disperse. Thermal inversion is stabilized by specific geographical features, especially nearby mountain. We have another pollutant, that is tropospheric ozone, that is a bad gas. Ground level ozone is a secondary air pollutant. and an important smog constituent. It is formed by complex chemical reaction of primary pollutants with oxygen. Its, its effect depends on the concentration in the air. At low concentration, it can be beneficial, as in fresh air after a storm. At higher concentrations, it is an irritant. Its concentration rises proportionately with that of the primary pollutant and is often reported as an indicator of smog accumulation in a city. So, air pollution control strategy. One is the post-combustion cleaning process. Sulfur oxide emissions are most often controlled by a chemical process called flue gas desulfurization. The gaseous combustion products are passed through a slurry of lime or calcium oxide to capture the sulfur trioxide. The device in which flue gas desulfurization takes place is called a scrubber. This process can be described by the reaction calcium oxide plus sulfur trioxide giving rise to calcium sulfate. The solid product is a wet sludge of calcium sulfate which can be disposed of easily. So, excuse me, flue gas desulfurization does not eliminate pollution. What it does accomplish is to convert a big problem, that is emission of large volumes of air contaminated by harmful level of gaseous SOx, into a small problem, that is collection and disposal of scrubber sludge. Problem with the flue desulfurization process. It's a system which is installed in a newly constructed power plant, represents about one-third of the total cost of the building of the entire plant, and energy is also required to operate an FGD system, meaning that for two otherwise comparable power plants, one with an FGD system will produce slightly less energy for cell than it would be obtained without the FGD system. For example, if the efficiency of a power plant without FGD is 37%, a comparable plant with an FGD system may have an efficiency of 33%. The investment in such a system, its maintenance and operation. Air pollution control strategies. Pre-combustion cleaning process. Pre-combustion cleaning is also a possible air pollution control strategy. For example, coal and petroleum can be treated chemically refined to remove sulfur before they are burnt. Coal gasification and coal liquefaction represents pre-combustion cleaning. Fuel switching. A fuel with a high sulfur content is replaced by a low sulfur fuel and reduce the SOx emissions. But low sulfur fuels have higher price. To reduce thermal NOx formation in motor vehicles is to add compounds containing oxygen to the gasoline. Another option is flue gas denitrogenation, a process analogous to flue gas desulfurization. One way to accomplish this is to inject some substances into the boiler or into the exhaust gas stream, which will react with and destroy the nitrogen oxides. An example is the use of ammonia, that is 6NO2 plus 8 molecules of ammonia will give rise to 7 molecules of nitrogen plus 12 molecules of water. The products of this reaction, nitrogen and water, are both harmless. Another way of control that we have already learned, that is removal of SOx from flue gas, removal of sulfur from fuel before burning, use of low sulfur fuel, and substitution of other energy sources of fuel combustion. So this is basically the four ways how to remove or how to reduce the uh, SOx emission. So this we have learned earlier also, that is SOx from the flue gas is usually eliminated by using chemical scrubbers. That is, the flue gas is passed through a slurry of limestone or calcium carbonate, and what we are getting is calcium sulfate. So calcium sulfate is a precipitate which can be actually taken off. An alternate process is based on a reaction between bisulfite ions and citrate ions. The flue gas is cooled to 50 degrees centigrade or lower and freed from particulates and traces of sulfuric acid, then passed to an absorption tower into a solution containing citrate ions. Sulfur dioxide plus water, sulfuric acid, and it will lead to bisulfate, and again it's reacting and producing something passed into a closed vessel where hydrogen sulfide is bubbled as a gas. So this is a very indirect mechanism of removal of sulfur through formation of hydrogen sulfide gas. Particulates can be removed from a number of techniques of varying degree of sophistication and cost. So cyclones, fabric filters, and electrostatic precipitators are the most common ones. Cyclones are simple devices as illustrated below, but are effective for removal of large particles only. Baghouses are somewhat similar in operation to the vacuum cleaner. So a stream of gas is made to pass through the fabric bags. The particulate matter is trapped in the pores of the fabric, and if the bags were never cleaned, eventually all the pores would plug up and trap the fly ash particles. To prevent this, the ash is removed either by vigorous shaking of the bags or by occasionally blowing a puff of air backwards through the baghouse and gently blowing the ash particles loose from the bags. In either case, the ash particles fall into the bottom of the baghouse, where they can be collected and removed for disposal. The use of electrostatic precipitators is the principal method available to the electric power industry to control fly ash emissions. A centrally mounted wire carries a strong negative electrical charge. The walls of an ESP have a strong positive charge. As fly ash particles are swept through the ESP by the stream of flue gas, the particles acquire a negative charge from the wire. The negatively charged ash particles migrate to the positively charged walls where they stick. Periodically, the walls of the ESP are cleaned. The dislodged ash falls to the bottom of the ESP, allowing periodical withdrawal for disposal. So these are all the methods for removal of these pollutants, or we can say the pollution control strategies are there, though we have certain advantages or disadvantages regarding this, but if they are used successfully, then the problem of generation of these pollutants can be mitigated to a large extent. So we have electrostatic precipitator, we have the catalytic converter, we have cyclone bags, we have electrostatic precipitator. So all these are actually giving rise to low emission of these pollutants. And the final way we can say is that switching to a alternative source of the fuel. So that will also be included in our upcoming lectures, that is alternate fuels, fuels based on bioproducts, which actually give rise to emission of zero pollutants or emission of very negligible amount of pollutants. So they can be alternate fuels, we are calling them as alternate fuels or biofuels. They can be of biodiesel, bioethanol, or products made from any of these these bioproducts like algae or agricultural waste. Being an agrarian country, we do have lots of amount of agricultural waste in our field, which can be converted successfully into the biofuels that will give rise to zero pollutants. Thank you.